All right, you guys, let's continue. Sorry, I didn't want to waste your time plugging in those values. It took a little bit longer. So for number 20, I got a 23.5. For 36.67 or 0.6, I got about a 28.7. And that's a 21.9. So it's one of those problems that says find the min or a max on a closed interval. We could do what we just talked about, to where we want to see if it wasn't on a closed interval, you found a critical number. How do you know this critical number is a minimum or a maximum, right? What you could do is find the second derivative. And now when you find the second derivative, you will get a negative 0.03 constant, yes, which is always negative. This is, by the way, if you think about it, it's a quadratic function with a negative coefficient. This function will look nothing other than this, right? So it's an upside down quadratic function, or an upside down parabola. So sure enough, the second derivative is always negative because it's concave down. So what happened at this one and only critical number? You're going to have your maximum, right? And as you also see from this other method, right, where we plug in the beginning, the end, and see which one, and the critical numbers in between, which one leads to the highest value? Clearly, the critical number in between, yes? So this is our answer. So it says, at what speed is fuel economy greatest? Our ultimate answer is at about 38.67 miles per hour, right? You're going to get what? You're going to be able to drive 28.7 miles for every gallon. Okay, so that's when you get the most mileage for your gas, right? Okay, now this next problem is definitely where it's getting started. So it says, what is the maximum possible area of a rectangle with a perimeter of 40 feet? By the way, in your section, you will also see a lot of problems like this that I've solved for you in the textbook. So as you see, I have to find a maximum. That means that's exactly what we're trying to find. Minimums, maximums, yes. But this time you do not have a function, right? You don't even have an interval that says from here to here. Okay, so how are we going to solve this problem? So this is what we want to do. We want to maximize what? An area. Okay, so this is the function we're supposed to maximize, the area of a rectangle. And this is our condition. So what I'm suggesting you do every time you solve a word problem that involves a geometry picture, a triangle, a rectangle, a circle, whatever it is, draw that. Okay. So there's a rectangle. What does a rectangle have? A rectangle has a length and a width. Or call it an X and a Y, it's up to you. Here, I'm just going to make it easy. And I'm going to make it, right, variables that we usually use. So instead of calling an L and a W, I'm going to call it an X and a Y. So let X be our length, and let Y be the width of this rectangle. Okay, so what do we want to do? We want to maximize the area. Great. What is the area of a rectangle? Well, the area of a rectangle is length times width. So it's X times Y. Great. What do we want to do with this area? We want to find its maximum. Okay. So the problem is, as you see, the area of this rectangle, if that's all I'm looking at, is a function that depends on two different quantities, right? It's not a function of one variable where I'm going to go and take derivatives, set them equal to 0, go through all the motions. This one has two variables, and what am I to do with that? We're not in chapter 4 yet, where, by the way, we will be able to deal with two variables. There's a second part of this problem that we haven't used. What's the problem? It says that the perimeter is 40 feet. Maybe we can use that. So what do I know about this rectangle? I know something I have to keep fixed. What I have to keep fixed is the perimeter at 40 feet. How do I find the perimeter of a rectangle? The perimeter is the sum of all the sides around. So when you add up all the sides, what do you get? You get 2 times the length, right? And you have 2 times the width all around. So there it is. We know the perimeter, though, must equal to what? 40. We know the value of it, which is perfect. So knowing this equation here, what I'm going to do is I'm going to solve this equation for y. So, in other words, 2y is going to equal to 40 minus 2x. Divide the whole thing by 2. So y is going to equal to 20, yes, minus x. Or 2x plus 2y is 40. Divide everything by 2 first if you want. So x plus y must be 20. So y must be 20 minus x. Why did I do that? Because now I don't know what to do with 2 variables. But if I could solve one in terms of the other, then look at that. What is the area going to equal to? I'm going to call it an a, by the way. Is x times, instead of y, what can I write? Well, 20 minus x. I know a condition about this x and the y, right? So this has to be satisfied. Whatever y is, apparently it has to equal to 20 minus x. So that makes it a nice thing because now I have a function that depends on one variable only, right? Okay. So basically we set up our function, okay? What do I want to do with this function? I want to find its maximum. So our story, just to go back really quick one more time. This one was easy. Why? Because the function was given. You didn't have to have a story that you had to manipulate, do something to make up the function, whose min or max you have to find. Out of this story, we were able to come up with a function. How? We're looking for the area. Great. How do you find area? Well, there's the formula. Yes? It's got 2 variables. That's a problem. Is there something else about this x and y? Yes. So this condition, we call it, we use it to solve y in terms of x, plug it in, and all of a sudden I got rid of one of the variables and I only have one left. So how do we find the maximum of any function? Well, we're looking for the critical numbers first. What are my critical numbers? Or how do I find them? Well, I'm going to find the derivative and set it equal to 0. What's the derivative? Is 20 minus the derivative of x squared is 2x. Okay? How do I find the critical numbers? Well, I set the derivative equal to 0. This is easily solved. X, by the way, is 10. Great. That's my critical number. Okay. Now, what do I do with it? Well, if I were to be given a beginning and an end, in other words, an interval, it has to be between so and so and so and so, right? I could just put in those 3 values, right? Beginning, end, and these critical numbers, and see which one leads me to my maximum possible, right? However, now that we couldn't come up with conditions, what could be some of my conditions? Well, the length can be less than 0, right? It has to be positive. So it certainly has to start at 0. By the way, it can be more than 20. Why? Because if it's more than 20, the width is going to turn up negative. So that's not possible. But we're just going to take the easy route instead of thinking about this. How do I know that my critical number is a minimum or a maximum? As we saw before, all I have to do is find the second derivative and see if the function's concave up or concave down at 10. So finding the second derivative gives me a negative 2, which again is a negative value. So that means what? The graph is always concave down. So this one critical number is going to be a maximum. Okay, so we found our maximum. Where does the maximum occur? At x equals to 10. By the way, again, this is a quadratic function. We already know. You've gone through a bunch of algebra before. How do we graph quadratic functions? The graphs are parabolas. Because the coefficient of x squared is a negative, right? The graph of this parabola is going to have to be upside down. So the one critical number you get where the tangent line is horizontal has to be a maximum, yes? So what is the maximum possible area? Well, we know it occurs when x is equal to 10, but it says to find the maximum area. So I'm going to write this down. So the maximum area is, all I have to do is plug, I know I'm going to get a maximum, right? So all I have to do is plug this 10 into the function, right? So it's 20 times 10 minus 10 squared. By the way, that's a 200 minus 100, which is 100 square feet. So that's your final answer. And how do I know? Because this was feet, so area is square feet, and we're done. So the maximum area is going to be 100 square feet. When does it occur? When x is 10. When the length is 10, by the way, the length is 10, what's going to be the width? Remember the width was 20 minus x, so 20 minus 10 is 10. And this is always really a story. If you want to maximize the area of a rectangle, you have to squish it into a square. So a square is a specific kind of rectangle. Don't tell me, oh my gosh, it's a square. I thought it was supposed to be a rectangle. Yes, a square is a specific, a particular type of a rectangle, one where the length is equal to the width. Okay. So let's continue with another word problem. As you see, there is no formula, so we need to come up with it. So let's read. So it says a firm is constructing an open top box with a square base and a volume of 108 cubic inches. So that's what we know. Kind of like we knew in the last problem that the perimeter had to be 40. So something is fixed. In this case, the volume is fixed. It says, what dimensions yield the minimum surface area? And what is that area? So we want to find the dimensions that will minimize the surface area. That's what we're trying to do, minimize the surface area. So we're going to have to come up with it first, okay? How? Well, as I suggested in the last problem, draw a picture. Okay, so we have a box. What does a box look like? Well, I'm going to try and draw a three-dimensional picture for you. On a two-dimensional space, which is your paper, or my paper, I should say. Okay, so what do I know about this box? I know that the base is a square. So what does that mean? That whatever we call the length is the same as the width. So the bottom has the same length and width. So let's call it an X, yes? Instead of call it length, length, or width, width, there you go. But it doesn't say that what? That the height is the same. So I'm going to have to use, yet again, a different variable, right? Y. Okay. So first things first. What do I know about this box? We know that the volume is 108 cubic inches. How do I find the volume of a box? Well, the volume is length times width times height. So x times y, which of course can be written for short x squared y. And what else do I know this volume to be? I know it to be 108. So again, that's the equivalent of last problems. The perimeter must be a fixed 40. The volume, okay, we labeled it, and now we have a formula for it. What do I want to do? I want to minimize the surface area of this box. Well, how do I find the area of this box? Now, the area of the box is all the sides, yes? So, first of all, I have a base, yes? The area of the base is length times width, so that's the base. It gives me an x squared. Plus, what else does my box have? My box has 4 sides. And now it starts getting crazy, but these 4 sides, what are their dimension? Length times width. That's a length times width, so again an x times y. So all sides, by the way, have a size of, or an area, an x times y. And we have 4, right? The 4 sides. And what's important is it's an open top, so there's nothing at the top. It's not another, it would be an x squared for the top if it was closed, right? The base and the top both are an x times an x, but we don't have a top. Okay, so again, what do we notice? We notice the function we're supposed to minimize has 2 variables, yes? We're going to use the same trick from before to do what? Take the top equation and solve it for y. Why? Again, because I like functions of x. Second of all, it definitely is a lot easier to solve for y than it is to solve for x. Okay, and what do I do with this y? I plug it in here. So instead of y, I'm going to write 108 over x squared. All right, so put this together. It's going to get me an x squared plus 108 times 4 is 432. And what's going to happen is one of the x's is going to cancel out. So it leaves me with an x on the bottom. Okay, all right, great. So now area is a function of x. I'll write it up for you one more time. It is x squared plus, by the way, I'm going to make that ready for derival. So in other words, for taking its derivative. And instead of having that fraction, the 432 over x, I'm going to write it as a 432 and bring the x up on top with a negative exponent. Okay, so we want to find its minimum. Yes, find minimum or maximum. What do? Take the derivative, which is going to be 2x minus 432. X to the 1 less than negative 1 is negative 2. Yes? What do I do with this function to find minimums or maximums? We set it equal to 0. Okay? All right, so for this, I'm going to turn this back into a fraction. It looks better. Okay? And what I'm even going to do is I'm going to throw the 432 over x squared fraction over to the other side. Okay, so you'll see this is going to come up many more times, and that's going to be the fastest way to solve these equations, so pay attention. And then what can I do with this? I can cross multiply, right? So this is a 2x over 1, if you can think about it. So the 2x gets multiplied to x squared, and the 432 gets multiplied to 1. So I'm going to take this aside here. So I'll get a 2x cubed is 432. Okay, and all of a sudden I don't have a fraction anymore. Get the x, divide by 2 both sides. So that's 216. Okay, the last thing to do to get to x is take the cube root. So x is going to, by the way, be 6. So we solved this equation. This is our critical number. Okay, great. Okay, now, one more time. How do I know that this critical number indeed will minimize my area? So if now I already found what dimensions, the x has to be 6, we could plug it in and find the y to it. So we'll figure this out in a second. But my question is, how do I know that I'm not lying and indeed at this value I'm going to get a maximum? So that's that second derivative test that says take the second derivative and see what happens. I'm going to use this version of it. 2x minus, wrong one. There's the derivative. It's like this looks familiar because I already did that. I'm taking the second derivative, so that's going to be a 2 plus 432x to the negative 3, right? What do? I want specifically to find the second derivative around this 6. So I'll know, is it going to be a maximum at 6? Yes. So in other words, was your function concave down here? Or is it a minimum? So was your function concave up? So we're looking at second derivative at 6. So that's going to be a 2 plus 432, by the way, over 6 cubed. Yes, that's what an x to the negative 3 is. And I don't even care to figure out the answer. As you see, these are now all positive values, so I know it's a positive, right? So a positive means at 6. Yes, I could look differently around it. But we know at 6 specifically, your function was looking up, right? It was a positive. So definitely that means we have a minimum value, yes? Just as we were asked for, right? We're minimizing the surface area at 6. Okay, so let's put it together. What are the dimensions? The base is 6 inches by 6 inches, right? So the base is 6 by 6. You can even go back and write it here. The height of this box, in other words, the y, is going to equal to what? How do I get the y? There is a y in terms of x. Is 108 divided by 6 squared, which is 36. So that's going to be 3 inches. Okay, so 6 times 6 times 3 is 108, by the way. And then it says also find the dimensions, we did, and also find the area. So how do I find the area? Well, I plug the values in. By the way, you all both have x and y at this point, so you can plug it into this version, or you can plug it into the version that only had the x in it. It doesn't matter, so I'll use this. So x squared, so that means 6 squared, plus 432 divided by 6. Put this in your calculator. And I have 108. It just so happened square inches. And here are the dimensions. Okay. So there it is. That's your problem. Okay. So I'm going to tell you something. Really, this part here is a little bit of a waste of time. And I really don't mind if you guys are going to start skipping it. And I'm going to tell you why. We're really not going to trick you. So all we're doing is basically with it what? Verifying. Is this really going to give you a minimum? Is this really going to give you a maximum as we asked for? I'm going to tell you we're never going to trick you. Yes, if it says maximum, the value you get, your critical number, will be a maximum. If it says minimize, yes, the critical number you're going to find will be where your minimum is reached. So you can skip that part, and we're going to do that in the next problem. It's a little bit a waste of time. I mean, you're supposed to, but it's always going to come out what it is. So I'm trying to save you some time. Okay. So maybe one more, and then we'll take a break. We'll finish the video on, or the section on our last video. It says, an open top box is to be created from a square piece of cardboard that measures 18 inches by 18 inches. Square piece of cardboard. That's 18 by 18. So that's, by the way, how you can make a box. It says, by removing a square from each corner. So in each corner, you cut out a square. And the same square in this corner, and the same square in this corner, and the same square in this corner. So when you cut out these little squares, what's going to happen is you can then fold up the sides. And these are your new sides. Okay. So just think about it. This piece is gone, so that's going to be one side when it comes up. This is going to be another side. Yes, so these pieces are gone. You remove them and you fold these, and these parts are going to come next to each other. So what you're going to get, these sides are going to come up and they're going to be right next to each other. So you got yourself a box. Okay, all right. So it says, what is the volume of the largest box that can be constructed? In other words, you're trying to make the largest possible volume. In other words, maximizing the volume. Okay, so how do I do that? Well, the question is, how am I going to cut these little corners in order to make this box big as possible? So if I cut small corners, the base is big, but the height is going to be, it's going to be pretty shallow, right? So the height won't bring much in. If I cut these a little bit more, yes, then the bottom is going to be pretty small, but it's going to be really high box. So in other words, how should I cut these corners in order for this volume to be a maximum? So what we need is a little X. So since we're cutting the same little squares, all those are going to be all the same, and some X by X. So in other words, should I cut an inch on each side? So should I cut 2 inches on each side? Yes. How much should I cut so that when I fold it up, this box has a maximum volume? The point is that no matter what I cut, this length here, right, and this box is going to be what? This one's going to be 18. I'll write it at the bottom. 18 minus 2x. And why is it 18 minus 2x? Because from the full on 18, yes, I cut an x on this side and an x on this side. What's the width of it? Well, again, it's 18 all the way, and I cut a little x and a little x. So that's also an 18 minus 2x. And I need one more thing for the volume. I need the height. What's the height? Is the little x that comes up. So easily enough, what's the volume of this box? Is length times width times height. Okay, so the nice thing is, is anything else given? No. And I don't need any other condition. Why? Because this whole function depends on one variable only. I don't need something extra that would allow me to solve y in terms of x, right? Because my function at the beginning had 2 variables. So this one already just has an x, so that's plenty. What I need to do is find the maximum of it. Great. So I'm going to have to distribute all this out, combine like terms. So I don't want to waste too much of your time. So there it is. Distribute. 18 times 18 is 324. Negative 36x minus 36x is negative 72x. Negative 2x times negative 2x is a 4x squared. And then distribute on another x, one more. So I'm going to get 324x minus 72x squared plus 4x cubed. Okay. All right. So how do I find the min or a max of a function? By now we've done so many. If I want to minimize or maximize something, I need to be looking at the critical numbers. Yes. So let's find the derivative. So that's the easy part. We've practiced many times. That's 324 minus 144x, right? 72 times 2 plus 4 times 3 is 12x squared. Great. What do I do with this? Set it equal to 0 and solve. I should have had it written in a different order, so I'm just going to rearrange it. So I'm going to have a 12, by the way, greatest common factor in them all, times an x squared minus 12 times 12 is 144. I swapped them in a different order. Plus, when you divide, you get a 27 times 12 is the 324. Okay, can we factor this some more? So numbers that multiply to 27 and add up to 12, that's easy. That's 9 and 3. Okay. So it looks to me like I'm going to get two critical numbers, x equals to 9 and x equals to 3. Well, that's a little bit bad, because how do I know which one to use? Of course, I can find a second derivative, yes, and see which one of these gives me a maximum. And again, what does it mean, a maximum? It means that, what does it mean, a maximum? It means that your second derivative there is negative, yes, so the function is concave down. But let's look at these values. Can x be 9, by the way? Do both these numbers make sense? By the way, if either one of these x's would have been a negative, I'd throw it out right away. Why? I can't cut a negative amount out of a box, yes? But they're both positive, yet one of them doesn't make sense. Which one? Now, if I cut a 9 on each side, how much do I have left for this? If each x is a 9, then 18 minus 2 times 9, by the way, yes, is a 0. So I cut the whole thing. I cut 9 inches here, 9 inches there. I cut the whole thing into 4 pieces. There's a box left from that, right? So that's why 9 doesn't make sense, right? So 3 does. And again, yes, I'll waste my time one last time. How do I know it's a maximum? I'll find the second derivative, which is, by the way, negative 144 plus 24x. And what do I check? I check if the second derivative at 3, what is it going to get me? It's going to get me negative 144 plus 24 times 3 is 72. The point is that's a negative, yes, when I plug in this critical number. So since the second derivative is a negative at my critical number, there, the graph was looking down. So I have a maximum. Duh, yeah, that's what I was asking for. So you're good, right? So don't worry about the second derivative test. That's all I'm telling you. Okay, let's answer the question. So we know what we have to do. We have to cut 3-inch squares from each side. So it says, be sure you always answer the question of the problem. So the question might not be, what is the dimension, right? What is the size? By the way, the first problem just said, what's the area? The second one said the dimensions and the area. So tell me what x you have to use and what answer you get. And this time it says, just find the volume. So in other words, plug in this 3 into the volume and see what's going to be the answer. And you can plug it into either one of these. I'll plug it into the top. So 18 minus 2 times 3, by the way, is 6. 18 minus 2 times 3, by the way, is 6. And then times another 3. So that's a 12 times 12 times 3, which is a 432 cubic inches. So that's the maximum volume that you could create. Okay? And that was your answer. Okay? All right. So we're going to take a break, and we have a little bit more 2 more problems to solve, but we're going to continue that on the next video.